Okay, good morning, everyone. My name is Brian Field. I'm with Comcast, and today I'm going to talk to you about some thinking that we're doing within Comcast related to IPv4 as a service. And I'm not sure if that's a term everyone's familiar with, so I'm going to give a real quick definition because that'll put into context kind of the rest of the talk. Kind of what we're thinking about doing is potentially running IPv4 as an overlay service on top of an IPv6 underlay network. And we think there's a number of reasons for doing that. I'm going to share with you the motivations from why you might want to do that, and then give you some analysis that we've done in the v4 space that kind of details how v4 is being used in our network today. And then I'm going to give you an architecture that we're working on here that would allow us to kind of, run a v4 overlay on top of a v6 infrastructure. And, listening to Russ's talk earlier today, it seems like, the thinking is kind of in parallel to what Russ is saying, in that we're basically running a control plane on top of another control plane. We think there may be some value in terms of doing that. Let's see. I always have problems with these things. Green one. Ah, green one. Thank you. All right. So I'm going to start off with the really highly scientific graph here, which basically shows, the relationship between v4 and v6 traffic in our network today. And clearly, we're way on the left-hand side of this, right, where we've got significantly more v4 traffic than v6 traffic. But at some point in the future, we will transition where we'll have more v6 traffic than v4. And so what we're starting to do is we're trying to think about, what might we want our network to look like after we've transitioned to where there's more v6 traffic than v4. Do we want it to look the same? Or can we do some optimizations? Can we start thinking about optimizations today so that, as we ask our vendors for new features and whatnot, or less features, that we're basically setting ourselves up for where we're going to be post that transition. So we're starting to think about, what is our network ecosystem going to look like? Or, what's the right way to build networks, when there's more v6 traffic than v4? And so kind of, we've gone through this before where we've had protocols that were deployed everywhere that have, basically gone away. I've listed a few of them here. Maybe CLNS should be included as well. But, we're kind of going through this evolutionary, sequence where we've had protocols that have been predominant, over time get subsumed or replaced by other protocols. And we think the same thing is going to happen for v4. Now, I'm not suggesting v4 is going to go away completely. But what I'm saying is that we may be able to, or maybe it makes sense to start thinking about what our network should work or how they should work and what they should look like when we get to the point where there's more v6 traffic than v4. Okay, so kind of what we're thinking about is building or driving towards a v6 optimized network. And so again, the thinking here is that we're not going to be lifting all of our v4 traffic on top of a v6 infrastructure today, but in the future, what might that look like? And so I'm going to give you a couple of concepts here to give you an idea as to how we think we're going to baby step in that general direction. The first one is this concept of a lean core. And so you can think of it as being a network where it's still dual stack, but what you're doing is you're looking to reduce the types of features that you've got there, and you're reducing the size of the fib. We think there's a value in terms of eliminating complexity by eliminating features that you're using, and that there's probably some significant cost savings if we can reduce the size of the fib. Right? Today we buy routers with millions of entries for fib for v4 and v6. And I'm going to share with you some data that basically says we're wasting a lot of money in that space. All right, so kind of we're initially thinking about transitioning our network to this lean core sort of concept. Now there's another concept here, and I think some service providers are going down this path today, where they're basically driving their infrastructure to be v6 only, right? So they're trying to eliminate v4 altogether and then run v4 as some sort of overlay on top of a v6 only network infrastructure. We're not trying to get there right now, but we see value in going in that path. And then you kind of think of a lean v6 core as kind of being the combination of the two, where it's really geared towards v6 and you're really gearing towards reducing the number of fib entries you need to carry in your network. And again, we're really targeting that first concept, this kind of lean core sort of concept. And again, we think there's really two primary values that are going to be had there. The first is that if we can eliminate different types of features that we don't really need, and if we get the vendors to kind of eliminate them from their code train, that's going to make, that's going to eliminate bugs and make our networks more robust. But we think that, if we can drive towards this model of having a thin fib, having fibs, on those ASICs that are significantly smaller in size, given how we basically build networks, that will reduce the cost of the memory for those ASICs. That'll reduce the amount of power we're putting into them. That'll reduce the amount of heat we need to cool on and whatnot. So again, we think there's a fair amount of value in terms of moving towards this leaner sort of architecture. And that's kind of what I'm going to talk about here in the next few minutes. And so as you think about moving down this path, if we're going to gear ourselves to try to move towards more v6 focused and more of a thin fib sort of architecture, but nonetheless we need to support v4, what's the practicality of that? Okay, so what we did earlier this year is we basically started doing an analysis of our network, of our v4 network. And basically, this is just showing us about 5 days back in February of the amount of traffic load on our network, the amount of v4 traffic load on our network. Chances are you've seen these graphs before. You may dream about them, right? This is the kind of classic kind of diurnal pattern of traffic on our networks today. Now, I've had to scrub the y-axis. The y-axis basically shows how much load, but what I can tell you is the y-axis is in terms of terabits a second, and then sometimes it's double-digit terabits per second. And that's going to be important, understanding the scale of this as I talk about subsequent information here. But basically, this is sort of the classic profile of how much v4 traffic we have in our network today. Now, this is really kind of probably a more interesting slide for you. What we did was we took the NetFlow data and we basically asked, how much traffic do we have for every v4 prefix that we're carrying in our fib today? On the backbone, on the Comcast backbone today, we have about 575,000 fib entries. So we're getting BGP updates from all of our peers, doing path selection and whatnot, and then programming the fib. And again, it's about 575,000 v4 prefixes in there. You notice that this graph here, which is basically showing how many prefixes we see in NetFlow over time, the maximum value there, the numbers are kind of poorly formatted, but that upper bound is 180,000. So what the data was immediately telling us is even though we're basically carrying all of these routes and all these prefixes and jamming into these fibs and asking for millions of fib entries from the routing vendors, we only basically send traffic to about 160,000 prefixes today, v4 prefixes today. So what that means is about 72%, and based on the study back in February, 72% of the fib entries that we're jamming into those ASICs aren't being used at all. 72%. Okay? So that was pretty eye-opening to us, right? That we have, again, we're asking routers to build bigger and bigger routers with, more ASICs for more entries and whatnot. And for the most part, we're not using a significant portion of them today. When you think about it, Comcast might be a bit of a special case in the sense of, we're based in North America, and so getting /24s from 10 or 12 time zones away, maybe it's not surprising, that we have a significant number of entries that we're not sending data to. But nonetheless, 72% of the entries have no measurable traffic. So that was pretty enlightening for us. So the next thing we want to do is kind of dig in a little bit more details as to those 160,000 prefixes. Those prefixes that did have measurable traffic, what do they look like? Do we have like a uniform distribution of traffic to the ones that do have measurable traffic, or is it exponential in some way as well? Okay, so this is detailing just those 160,000 prefixes. And basically, think this is what we effectively did. Think of, getting 160,000 prefixes where for every prefix you have a certain amount of load and sort them. And then what you do is you basically go to the prefix with the most amount of traffic, and you start working your way down, adding up the amounts of load until you get the number of prefixes that account for 90% of the load, okay? And so what that 90% point it means, and that's going to be the number about 3,200, basically what that is telling us is that on the Comcast backbone, to carry 90% of the v4 load, I only need 3,200 prefixes. Now that's a mix of Comcast prefixes and internet prefixes, and so the green line basically shows how much of that is made up of Comcast prefixes versus internet prefixes. So in order to carry 90% of my v4 load in the underlay fib, I would need about 3,200 prefixes. About 2,300 of those would be Comcast prefixes, and about 900 would be internet prefixes. Again, think about this. We're buying line cards with a million of entries for fibs, and a significant portion of the traffic is handled by a very small number of prefixes. Now, this is the 90% point. So, if I was going to think about building an overlay and an underlay, and I was going to carry 90% in the underlay and 10% in the overlay, well, remember that first slide I showed you, that first graph I showed you where I mentioned double-digit terabits per second? So 10% of double-digit terabit per second still results in terabits per second. So maybe not quite ready to do that yet, because again, part of what we want to do here is transition this into an overlay that's based on cloud infrastructure. That's a key part of what we want to do here. So if you look a little bit further to the right, basically what we did was we identified the 99% point. And again, it's the list of prefixes sorted, from most to least, and basically identifying how many prefixes carry 99% of the load. And it turns out that you only need about 26,000 prefixes, at least from the Comcast view of the world. You only need about 26,000 prefixes to carry 99% of the load in the Comcast network. And about 6,000 of those, of the 26,000 are Comcast prefixes, and about 20,000 now are internet prefixes. Okay, so it seems, at least to us, that this is pretty enlightening. That again, we're building, you're asking these vendors for huge amounts of memory to store huge amounts of fib entries for v4, and we're not using most of it. And you know what? Remember that very first graph, which is basically showing over time that we're going to have more v6 traffic to v4. Do we want to continue going down this path, or can we do things more efficiently? And so our thinking is, maybe we need to rethink how we're doing our networks here. Okay, so I've kind of summarized it here. Again, 575,000 v4 fib entries, 72% don't carry any traffic at all, or don't pull any traffic at all. And then out of the ones that are pulling traffic, basically 99% of the traffic load is identified by about 5% of the prefixes that we're putting into the fib. So there's a huge amount of waste. And then kind of thinking of it the other way, we have 550,000 or 549,000 prefixes that exist that only carry 1% of the load. Okay? So what we think is doing IPv4 as a service is in fact practical today. Okay? Maybe not for all v4, but we think we can make a substantial reduction in terms of how many entries we need to put into the fib by lifting a significant portion of the v4 prefixes out of the underlay network and into an overlay sort of network that's built on cloud infrastructure. Now that's not going to help us today, right? We've already purchased routers that can handle all of these fib entries and whatnot. But what it can do is allow us to kind of validate that this approach makes sense, and that this approach scales and it is in fact robust, right? And this is sort of, again, what I think Russ was hinting at is these overlays of control planes. This is kind of what we're thinking about doing as well. So this kind of allows us to kind of validate this approach so that we can go back to the vendors and say, you know what, we would really like, a v6 focused platform, and we don't need as much memory on those line cards because it is practical to build an overlay today. And the other value here is that not only does it help send a message to the existing vendors, but maybe it also lowers the bound for new people to get into this space in terms of building forwarding infrastructure as well. If we can reduce what they need to do to become part of a big service provider network. Okay? All right, so basically, I've given you a little bit of motivation here, as to why we think moving down a v6 focused network makes sense. I've given you some analysis here as to kind of how v4, at least from our perspective, how we see it being used in the network today. And now I'm going to talk about the mechanisms for how we might build an IPv4 overlay network. Okay, so many different ways you can do this, and I'm only going to talk about two technologies. And these are really two technologies that were of interest to a number of folks within Comcast. And I'm not going to go into detail here because I believe these two technologies have been talked about both here, NANOG and IETF, and elsewhere in a lot of detail. So I'm going to talk to you about these from two distinct ways. And when you think about building an overlay network really consists of two pivot points, the technology. The first is how you do encapsulation. So how do you take, in our case, a v4 packet and map it into a v6 packet? And so there's differences between how MAP, MAPE, MAPT, and Lisp work in that sense. And so the classic way you do encapsulation, and this is the way MAPE works and the way Lisp works, is where you take a v4 packet, and you basically totally encapsulate that v4 packet inside of a v6 packet with a v6 header. MAPT works a little bit differently. MAPT works in the sense of what it does is it basically looks at the v4 header and synthesizes a new v6 header. So it basically looks at the information, the address fields in the v4 header, and basically derives what the corresponding v6 addresses should be. And so what's on the wire for MAPT is in fact slightly smaller than what you'd see for MAPE or Lisp, because it's not doing full encapsulation. It's basically taking the v4 payload and then slapping a v6 header on top of it. There's no v4 header there. So that makes the MAPT approach simpler than MAPE or Lisp, in the sense it's simpler that it's smaller. But encapsulation is just one part of this. The other part of this is how do you determine when you encapsulate the packet, how do you determine where to throw that packet to? What's the endpoint at which you're going to send it to? And so this is where the map solutions tend to be different from Lisp. The map solutions tend to be more provisioning based, more set of rules that you basically apply to the border router, the home gateway in advance, which basically give it the information it needs to know to determine what the remote endpoint to send the packet to. And Lisp, and I'm going to use a slightly different term now, classic Lisp does something else, where they've got a control plane that's kind of based on DNS. Again, I'm not sure if people are familiar with kind of classic Lisp in the sense of, it proposed a mechanism much like DNS where you do a lookup for a packet or for an address to determine, what the remote endpoint was going to be for it. So classic Lisp does this kind of DNS kind of recursive sort of lookup to find, the remote endpoint in which you should be sending the traffic to, and it does some caching and whatnot to make that efficient and some probing to deal with, endpoints going away. So the two differences, between these technologies, again, encapsulation and what the mechanism is you're using to determine the remote endpoint to. In our case, we wanted to go down the Lisp path. We thought Lisp was the promising path. So the rest of the talk is going to be talking about the Lisp solution, but with a twist. Okay, so we're doing Lisp encapsulation, but we weren't yet ready or comfortable to basically move down the path of changing routing from this push-based routing model to kind of a pull-based query model. So what we did was we took our Lisp implementation that we got from Dino, wherever he might be, and we basically coupled it together with routing. Okay, so what we're thinking again is we're using the Lisp encapsulation mechanism, but we're still going to use our classic routing sort of paradigm. We're comfortable with that, and when we think about building this overlay, it would be easier to do, easier to operationalize if we basically kept a kind of common routing paradigm in place. And so, our thinking is that we're going to be doing Lisp encapsulation, but we're going to be using classic routing as the means to kind of program the information that Lisp is going to be using for forwarding information. And key here is that, cloud and virtualization is going to be the enabler here. We're looking to lift this overlay into our cloud ecosystem. And this is going to be enabled because, and this is where we have the two diagrams here. Today in the Comcast footprint, we have cloud and virtualization at the national data center level, and now we're starting to bring it into the high levels of the regional data center levels. We think and feel, and this is going to happen, where we're going to be pulling cloud and virtualization basically all the way down into the hub site, so down to where we have the CMTS is located today. And it's the fact that we're pulling this cloud and virtualization down, very much to the customer edge, that's going to be an enabler for us to basically bring or instantiate or begin our IPv4 as a service at that point. Okay, so cloud and virtualization here is going to be key for us. And again, what we're trying to do is leverage open source as much as we can, and where we don't quite have open source, we're growing our own code as we need to. Okay, so this is kind of a high-level architecture. I'm going to get into some details in the subsequent slides here. But basically at the top, I've got our other providers. I've got my backbone where I've got my peering routers and whatnot. And my regional networks, my hub routers, and CMTS. That's kind of the classic underlay infrastructure. That's what we have today. And what we envision doing is having an overlay network where we're going to have virtual machines running on that cloud infrastructure tied into our peering routers, basically at the top of our networks, and then also having VMs performing Lisp encapsulation that are very close to the customers down in the hub site. So in Lisp speak, they're going to be ETRs, egress tunnel routers, and ITRs, ingress tunnel routers. Kind of again, most of the analysis that we've done here was based on showing that a significant number of routes that don't pull traffic are internet routes. And so we're thinking initially that this Lisp paradigm, or IPv4 as a service overlay paradigm, would basically operate in one direction, namely outbound. Okay, that's kind of how we're thinking about getting this going from the beginning. And so you could imagine in regional networks, we'd have a number of ITRs pulling traffic in and a number of ETRs basically at our peering locations. So this is kind of like intended to give you a high level of what the actual architecture is going to look like. Now this is a little bit more details on how the routing is going to work. Okay, so it's more or less the same sort of paradigm if you look on the left-hand side there. I've got my routes coming in from my providers coming into my peering router, and then basically my peering router is going to basically identify which of those prefixes are really the heavy hitter kind of prefixes. What are the ones that have huge amounts of load to them, and we're going to allow those to flow down through our backbone, down through our metro networks, down into the hub sites. Okay, so those are the underlying prefixes. Those are the 26,000 prefixes I've talked to you about, or 50,000 prefixes, whatever you want. But those are the prefixes that have significant load on them. Our peering edge router will basically take all of the routes that's coming into it and then basically send them over to an ETR, these egress tunnel routers. And then these egress tunnel routers will basically send them to a route reflector and, dare I say, maybe a controller or something like that can apply business logic. And again, this is sort of where it ties into what Russ was talking about, right? We've got this overlay control plane and this business logic that sits on top of that. That's sort of embodied here, though I didn't split it out specifically. But we've got something acting at the control plane, doing some sort of route reflection or whatnot. Maybe it's doing something more sophisticated than that. And then it's sending those routes down to the ITR, down into each of the hub sites or each of the regional networks. And then what that ITR is going to do is going to inject a default. And so what you can imagine here is that, I'm going to be allowing those heavy hitter prefixes coming down, and that's where my knobs are, right? By the prefixes that I'm allowing to come down in the underlay, that's going to dictate what flows over the underlay or what gets pulled in over the overlay itself. Okay? Now, what I'm proposing here is, effectively, we want to build a v4 overlay on top of v6. So logically, when you think about it, I want a v4 prefixed with a v6 next hop. That doesn't exist today. Now, I know there's an internet draft out there somewhere, some form, that is basically proposing exactly this, to basically allow you to specify a v4 prefix with a v6 next hop. As far as I know, there's not publicly available code to do that. Now, what we wanted to do, and this is going to tie into some of the other thinking that we've shared here in NANOG in the last couple of years, is that we think there really is value moving control planes for new kinds of technologies away from classic BGP bits and bytes and TLVs to instead use JSON. And so it turns out, and I think it was the Google guys, not the Google guys here before me, but someone from Google or a set of folks from Google have written something called EXA-BGP. I don't know if folks are familiar with it. It's pretty slick. What EXA-BGP allows you to do is to basically speak classic BGP to, say, a classic BGP component, but on the other side, it can spit out BGP information in JSON. Okay, and that's basically what this is showing us. This is basically the EXA-BGP code here in JSON. It's a BGP update. You'll recognize all the information here, but it's represented in JSON as opposed to classic BGP TLVs. And the beauty of it being in JSON is the following. The beauty is that it's very easy to extend this, right? It's very easy for me to add new attributes, new information that may not be part of classic BGP, but allows me to experiment or test out new ideas. Again, back to Russ's experimental sort of concept. And so what we did was we took the EXA-BGP output. We have an ETR, effectively, that speaks classic BGP to our peering router, and then it spits out JSON BGP updates, to an entity, a piece of software that we've written. And what that does is basically just add a next hop value, a v6 next hop value. Right, so we've got JSON of the original BGP update in v4, and we take that JSON information, we add a few more attributes that indicate things like what the v6 next hop should be, and then we basically push that northbound to a route reflector. And today we're doing this via HTTP. Okay? But we wanted to show that the fact that it is in BGP allows you to extend things much more easily than trying to shoehorn things into classic BGP itself. Okay, so this is just kind of more of a theoretical, and again, I've had to remove kind of the y-axis details, and maybe this is pretty straightforward. But each of those lines there, the red line indicates how much load you would have on the underlay network, for different fib sizes. So, I believe the numbers are, the red line is 20,000 fib entries. So if your underlay was limited to 20,000 fib entries, this basically shows you, how much load you would have in the underlay. And obviously, as you allow the fib sizes to grow and more traffic to be pulled on the underlay, the curves get flat and go down. Okay. Okay, so kind of to wrap it up here. So what are we doing? We're trying to think about, what this futuristic network architecture should look like. Again, as we're slowly transitioning more traffic from V4 to V6, we're thinking about what do we want our network ecosystem look like in the future. And so we're thinking about, building an IPv4 as a service overlay network to kind of, get us, to be more efficient in terms of our underlying infrastructure. And we think of this as almost as beginning the beginning of transitioning services out of the kind of classic underlay network and into the cloud. Okay? And V4 is one of the first services that we're thinking about doing that. And there's value here again because it empowers us as service providers to kind of do the things that we need to do without having to go to the vendors and ask them to build features for us. So we find a lot of value in terms of doing that. And there's the kind of classic SDN paradigm. Do we program the network or do we make it lean? Today I think, at least from my perspective, it really makes sense to make the underlay network lean. Fewer features, fewer fib entries, and move complexity into the cloud where we have more ability to kind of manage it. And then just one observation here again, with SDN you have the network and cloud kind of combining. One of the learnings that we had here, is that OpenStack evolved out of the data center space. And so they're still playing a little bit of catch up in the networking space. So one of the things we realized was kind of OpenStack wasn't quite ready to kind of do or to support some of the features that we needed to do this IPv4 as an overlay. Now, Kilo just came out in April, and it sounds like Kilo might have the features, but we haven't got a chance to really look at it. But there's still some catch up that the OpenStack folks are doing to kind of get us to this point, to get us to the point where we really do network services on top of cloud infrastructure. And then just one other slide here. This is, I guess, the third time I've been to NANOG in June to kind of present. And I just wanted to kind of connect the dots because I think these things do really connect together. And again, 2 years ago, I was here up on the stage here proposing, it makes sense, or we believe it makes sense to start transitioning control planes to kind of be more JSON and HTTP oriented. And again, it looks like other service providers are going down that same path. Google went out and built ExaBGP. I don't know if it was specifically to support JSON or just as a means of doing troubleshooting, but there seems to be a little bit more energy behind kind of reevaluating how we do control planes. And maybe this touches again back on what Russ was talking about. So we think there's control plane evolution, clearly control plane evolution that we're leveraging today. Last year we were proposing or talking about what we were calling this hybrid router platform architecture, the ability within a component router to basically add your own operator-specific code. And we proposed or we demonstrated last year writing segment or building our own version of segment routing and running on the box, and actually dropping in our own version of ISIS as well. So that was kind of like legacy or platform evolution within the box. And kind of what we're suggesting today, we think, is really kind of like an end-to-end kind of evolution, where now we're basically refining the sets of services that are happening within the network ecosystem and then lifting the ones we really need to have more agility to and putting them into the cloud. Okay? All right. So that's my talk. Thank you much for your time. Hold on.
Hi, Brian. Alan Durant from ICANN. I would like to make a comment and a question then for you. The comment is about a very futuristic technology that was made in 2009. It's in RFC 5512 and 5565 that talks about how you can have an AFI and a SAFI in BGP that are different address families. So it was then done because some of our friends from CERNET in China had an IPv6 only backbone, and they wanted to route BGP for the IPv4 universities. So the first one described the AFI-SAFI, and the second one described a framework, and now this is all done. Okay. How is this implemented with various vendors? I'm not quite sure about. Different vendors have done different routes there, but right. The actual technology exists. It has been implemented, at least in China.
Okay, great, thanks.
The second is a question. It's about the number of prefixes. How many prefixes do you foresee in an IPv6 mostly world? I've heard different comments. People saying it's going to be really small. People think it's going to be about the same as V4. There's no difference. What's your take on it?
So I think the thinking is that we think it's not going to be nearly as bad as V4 today. and maybe not as well as we would like it to be kind of like in Cherry Pie v6 space. So I think it's going to be somewhere in between. But the thinking would be, that we're not, or hopefully not going to need to do as much kind of, or we're not going to have been going down the same evolutionary path that we went with v4, CIDR, pre-CIDR, all those sorts of issues. So hopefully we'll have built, an addressing plan that is much more scalable with fewer prefixes.
Thank you.
Yeah.
Randy Bush, IJ. The 70-odd% reduction in fib size is gained by a very trivial hack, which won the IRTF ANR award, SIGCOM awards, et cetera, called Dragon. And it's essentially the reduction of routing entries that are redundant and real cheap. Talk to your vendor, and we can all get this without JSON.
Okay, thank you.
Hannes Goedler, Juniper. Thanks for the data on the prefix traffic distribution. I knew that it was uneven, but I didn't know that it was that bad. A question to you, actually. Do you think it would make sense to build forwarding planes entirely different and incorporating memory hierarchies? I mean, the reason why fibs are so expensive today is because we are using SRAMs in order to produce 2 million fib entries. And just take a look at your laptop, right? There's a hierarchy of memory. There's L1 cache, L2 cache, DRAM. Do you think it would make sense to build in memory hierarchies in forwarding engines as well in order to tackle the cost problem there?
Yeah, it may. And I think it depends, in terms of how we were going to take the network moving forward. How much of the services do we want to put into the cloud makes sense to put into cloud? How much of it we need to remain in the underlay network itself? So certainly it couldn't hurt to continue or look at those technologies.
Because on the locality thing, I mean, we have the problem not just for v4. We see the same thing on certain GRE tunnels, certain MPLS entries, certain v6 routes, also having those power law distributions.
Right. And again, I don't know if, with Russ, again, what he was saying, with the centralized controller and whatnot, and I'm not suggesting we go down that path, but I think there's a desire from service providers, to kind of, have more ability to manage kind of what's happening in the network. And in the process, can we eliminate what's happening there? And so the paradigm, when I was thinking about this, it's as if, even with the hierarchical stuff, it's like, we're asking the vendors to build like a concrete highway to every Taco Bell, 7-Eleven, and Pizza Hut that's going to be made in the entire world. And for the most part, we're not using most of those lanes because you go to the Pizza Hut nearby, right? So we can maybe solve this via other mechanisms. But again, I question, is that the right paradigm, or do we think about solving it differently? But I'm not saying not to investigate that path.
Okay, right, point taken. Thank you.
Yeah.
Jeff Houston, APNIC. Look, I was kind of curious about your comment about fib. And I'm kind of wondering if it's the size or the speed that is really the issue with fib.
And the cross point is the cost then, right?
Well, cost, number of gates, that size.
Right.
Speed is something that's really hard to buy.
Right.
Because at some point you just can't go any faster.
Right.
And realistically, is speed the problem here as distinct from size?
So I think it's the two combined together.
Okay. And in v6, when in essence you're going to use 128-bit wide fib entries, which is 4 times the size.
So hopefully we've got many more fewer entries in the fib, right?
4 times fewer. Good luck.
Thank you. Yes.
I was Phil Rosenthal from IS Prime. I was wondering if you had given any thought to I don't know how many people in the room remember the SQL Slammer worm a decade ago. In the case where you have something like that, where you're now sending packets to every single IP address on the internet at random, what happens when you're now, you no longer have, really fast SRAM for processing, that?
Right. Yeah, we haven't looked at that. So. Oh, I'm sorry.
Yes, Paolo Lucente, speaking with my PMSCT.NET hat. I wanted to thank you for sharing the results of your IPv4 prefixes analysis. With David Barroso from Spotify, we did present recently a similar analysis that we did, but of course from the Spotify network. So it was very interesting to see that both from a content provider and from eyeballs provider, so I would regard Comcast and eyeballs provider, we have very similar results. So I was tending to think that the very low entries that we did see, so the 99% was 16K prefixes. I was thinking that's because it's a content provider with any cast and things like that. But actually you come up with very similar results. So that is very interesting. Great. I think there was nothing like that public before, so very good. And I have a second comment, which is you mentioned the ExaBGP. I wanted just to make the attribution right. So ExaBGP is from Thomas Manzing from Exa Networks in the UK, and absolutely not from Google.
Okay, thank you.
Thanks.
Yeah.
Just one more, please. And then
Bill Goldstein, retired from AT&T, but here on my own, representing only myself. First, forgive perhaps a dumb question to a very smart presentation. Are there any security schemes out there like deep packet inspection being run in perhaps not in provider networks, but in large customer networks that might reject your encapsulated packets?
So the encapsulation is purely within the Comcast footprint. So it would come in from our customers as a normal v4 packet, and then it would spit out on the other side as a normal v4 packet.
Okay, all right, well, I'm sorry, it was a dumb question. The second question is, I personally, I like what you have here, but are there any minimum standards or that have to be added in the large-scale provider networks, which you and we all depend on, in order to enable your encapsulation scheme in Lisp here?
So no, I mean, all the Lisp encapsulation stuff is well documented in RFCs today. Mm-hmm. So, and again, there's a number of open source implementations of that.
Okay, thank you.
Okay. Thank you very much, Brian. So.